Roll, actually.
Welcome to our 2024 Technical Design and Flight Readiness Review. We are the Aerial Robotics Club at NC State, and this year we are proud to present our new airframe, Kavik. Compared to Aquila, Kavik takes advantage of the more cambered NACA 6412 airfoil for its lifting surfaces and utilizes carbon fiber wings. Our new airframe comes packed with multiple quality of life improvements integrated into the design. For example, a simplification of the tail shapes allows for a much faster rebuild time. An expanded fuselage allows for nicer management of wiring for the placement of Kavik's modules, which have been placed with ease of access in mind. Kavik comes out to a gross weight of 42.5 pounds and is expected to cruise at 40 knots with a stall speed of 27.5 knots. Kavik is powered by the T-Motor AT8020 at 180 kV, which is equivalent to a 55cc engine, and it's also run entirely using two 6S 16 amp-hour batteries rather than a gas-powered engine like Aquila. A 23x10 XOR wood propeller accompanies the motor, with a pusher design of Aquila being retained. Operating Kavik on the flight line is our competition team. Gray will serve as our safety pilot, Hailey will be controlling autopilot, Jason will be leading ground station control, and our development team will have contributed many hours in getting Kavik ready to fly.
Our initial requirements were based on the constraints provided by the competition rules, as shown here. This chart includes our design choices that meet the constraints set by the competition rules. This chart below shows all the requirements as per competition rules and the criteria that must be met for us to consider these criteria successful. The aircraft is composed of four subsystems: the airframe, payload drop system, electrical systems, and software systems. The airframe is operated by the safety pilot or the autopilot operator and is responsible for flying the waypoint course and transporting the water bottles. The airframe consists of the lifting surfaces, control surfaces, propulsion, and modules, which can be seen in the diagram below. The payload drop system is controlled by the image recognition system and the autopilot operator. Each payload is released at a specific waypoint determined by the image recognition system. Each water bottle is attached to its own capsule, which activates a delayed parachute release mechanism once dropped. The electrical subsystem is responsible for providing power and autopilot connections to all parts of the airframe. 3 sets of batteries are used, one for payload, one for controls, and one for propulsion. The electrical subsystem of the aircraft ensures power is distributed to the necessary endpoints for a functional flight. The avionics module is designed to provide the autopilot system the necessary data over telemetry. The software subsystem consists of communication and image downlinking processes. Within the avionics module, a GoPro is used for imagery, and a radar dish is used to downlink images to the ground. Imagery and downlinking is constantly performed as the plane flies in autopilot. The ground station operator monitors the imagery and downlinking process while the plane flies its waypoint course.
First, a video is taken using a GoPro Hero 11 at a resolution of 5312 by 2988. This video is then transferred to the onboard flight computer, which separates out select frames and injects telemetry metadata, such as the location and orientation of the plane. You can see here an example of one of those frames, with the targets annotated. Each one gets around 30 pixels to a side, which is enough to distinguish the key characteristics of that target. A connection is established between the ground and the plane using a large dish antenna, and communication occurs in the 5G frequency range. There is an HTTP endpoint hosted on the ground PC, and when the flight computer processes a new image, it will send a PUT request to that endpoint that contains that image. This system allows us to send roughly 2 uncompressed images per second with very high reliability. The database, front-end, back-end, and automatic target recognition processes are hosted in Docker containers for portability, and once the images are on the ground, they are stored in the MinIO database. From there, they are sent to the automatic target recognition process, which uses a fine-tuned version of YOLO V8 to find and classify targets. The location and type of the targets is also stored in the image metadata and put back into the database. This YOLO V8 model was fine-tuned using synthetic data. We found it challenging to generate enough variation in our training data off of our home airfield and the targets we print out alone, so we used Stable Diffusion in Blender to generate images with that required variation. With the automatic system, we achieved accuracy of 99% on locating the targets and mid-90s on all the different characteristics of the targets. But because reliability is more important than absolute correctness, and there will probably be conditions at competition that we haven't accounted for in training this model, keeping a human in the loop ensures maximum reliability. The The human operator connects to the front end from the browser, which displays the images, with the targets highlighted and text showing the predicted type. The human then will make any edits to either the bounding box location of the targets or the classification. Geographic locations of the targets are calculated by the backend based on pixel coordinates in tandem with the indirect telemetry data. A drop point is calculated and inputted as a waypoint in the mission planning software. This entire process has been thoroughly tested at flights that are similar to that of competitions.
A delayed release parachute capsule slows down the water bottle to safe landing speed without compromising accuracy from wind gusts. The delayed release capsule is modular and 3D printed from PLA filament for convenient assembly and disassembly. Each capsule has a mesh sleeve to secure the water bottles to the capsule. A small flap is fastened below each bottle with a brightly colored string, allowing the judges to easily access and remove the bottle after it drops. As Kavik is flying, imagery is constantly performing target acquisition in order to determine where to drop the payload. Inside the fuselage, each bottle sits inside an internal drop module made of laser-cut wood and 3D printed PLA tubes to hold each bottle. A lever arm is locked in place by an extended linear actuator, which retracts from a PWM signal, releasing the bottle capsule. A limit switch on the drop capsule is compressed by the inside of the drop tube, keeping the built-in delayed release timer from beginning its countdown. A custom-made PCB powered by a 500 mAh 7.4 volt 2-cell battery is responsible for arming the delayed release timer and controlling the servo arm holding the parachute. A 0.1 second time delay is implemented with an Arduino to account for turbulence or abnormal vibrations inside the drop tubes that may cause the limit switch to disconnect and prematurely start the drop timer inside the plane. The bottle is set to be dropped around 92 feet laterally from the target, calculated by inverse kinematics, requiring a half-second parachute release delay before the target while cruising at 42.5 knots. When the plane reaches the drop location, the flight computer sends a PWM signal to the linear actuator in the drop module, causing the payload to release. As soon as it exits the plane, the limit switch fully depresses, starting the half-second timer. The payload falls approximately 150 feet, reaching a speed of 50 feet per second before the servo arm rotates and allows the parachute to release. To avoid FOD, the parachute and parachute cover are both tied to the top of the capsule. The 18-inch parachute slows the payload down to a safe landing speed of approximately 10 feet per second. Testing was conducted from an airspeed of 0 knots from a custom-built quadcopter and from competition speed out of Kavik.
Communication between the plane and the ground is accomplished by 3 separate radio systems. The first is a 900 MHz radio connection, which is used to transmit telemetry data from the plane to the ground station, as well as upload waypoint paths and parameters from the ground station to the plane. Each wing is equipped with a dipole antenna attached at the tip to allow for redundancy in the case that one antenna or connection fails. The second radio system is a 2.4 GHz link between the safety pilot's transmitter and a receiver connected to the aircraft's autopilot, which allows for manual flight of the aircraft. The third system is a 5 GHz Wi-Fi link between the plane and the ground station. The avionics module contains a Ubiquity rocket radio, which is connected to the flight computer. This link transmits images and other data from the computer to a 5 GHz dish antenna on the ground. The data received by the dish antenna is then transferred to our ground station computer via Ethernet cable.
Shown here is a block diagram of our communication system. The connection has a tested range of 700 feet. Beyond that, we could sustain a connection with the antenna equipment, but successful antenna tracking of the plane becomes more difficult. We hover around 3% packet loss, with that varying as high as 10% under normal conditions depending on the tracking of the dish and distance. Our dish statistics are shown below. These numbers vary somewhat with range and alignment of the dish, but for a reasonable flight, these are what we expect to get and what we have tested to get. Our testing procedure for the image downlinking system consists of launching the plane and flying an extended mission route, tracking distance, throughput, packet loss, and uptime. We also ran a test with no antenna tracking to simulate if the automatic system failed, and an operator had to fix it in one direction and leave it. At every flight test, we logged packet loss during the flights. The success is one where it stays below 10%, and we are able to downlink images in a reasonable amount of time. Overall, this image downlinking system is reliable and fast.
For the 2024 SUAS competition, ARC will be flying Kavik, a brand new airframe that makes quality of life improvements from the previous airframe Aquila. Kavik is a twin-tail fixed wing with a pusher configuration. The wings and tails feature carbon fiber composites laid up on foam cores. The aircraft has 2 ailerons, 2 flaps, 2 elevators, and 2 rudders, with redundancy built into the elevators and rudders, as each control surface is managed by an independent servo. The wings use a NACA 6412 airfoil, in which the larger camber provides a higher CLmax, which allows Kavik to cruise and land at a slower speed. NACA 0012 airfoils are used for the vertical tails, and NACA 0010 is used for the horizontal tail, to provide high stability and versatility. 2 6S 16,000 mAh LiPo batteries are connected in series, which power a T motor AT8020 at 180 kV. Here's a chart that details our analysis for selecting our motor and propeller combination. Our propulsion system will provide 25 minutes of cruising flight per recharge. Here's a diagram that shows our constraint performance analysis comparing the wing loading with the thrust to weight. It can be seen that thrust to weight of 0.4 with the wing loading of 21.28 meets all requirements for a successful flight within the competition rules. Here is a summary of our stability margins for Kavik, given the three types of weight loadings we expect. A full payload, semi-payload, and no payload are all considered as bottles are released during flight. In an attempt to decrease the complexity of manufacturing Kavik, the wings contain no twist, taper, or dihedral angle. Tails feature simple geometries which make rapid prototyping easier, and the increased width and height in the fuselage give more room for payload modules and wiring management. Kavik's wings and tails are manufactured with insulation foam cores cut with a hot wire foam cutter that does not require any CNC milling. Foam cores are laid up with a 2-ply carbon composite, with one layer being a 2.59 ounce spread toe and a 3.7 ounce 2x2 twill. That foam was used to generate G-code for the hot wire, cutting the wing and tail foam into segments. An enlarged tricycle landing gear is used to give clearance for the 23x10 propeller during takeoff. The fuselage is built from a laser-cut aircraft-grade poplar and birch plywood as well as its modules. The fuselage exterior is covered with non-permeable, smooth ultracoat, and PLA is used for 3D printed components such as the nose cone. Here's a final summary of Kavik's statistics.
Kavik uses a pixel cube running ArduPilot for its autopilot system. For our ground station software, we use Mission Planner. For autonomous flight, we are able to create waypoint paths in Mission Planner and upload them to the Pixhawk via USB or radio link. This software also lets us modify parameters such as cruising speed, control surface deflection, and autopilot aggressiveness, allowing us to tune our autonomous flight characteristics. We also use Mission Planner to activate our drop system autonomously by activating servo outputs at specific points on our flight path, which are then sent to the flight computer and redirected to our drop PCB. Finally, we have several fail-safes coded into our parameters, which gives us a safety buffer if we encounter errors such as losing radio connection. During testing, we made a total of 10 flights with a total flight time of 60 minutes and 7 seconds. Of these flights, 3 were purely manual, while the other 7 included portions of autonomous flight. In total, we spent 23 minutes and 15 seconds in autonomous flight and 36 minutes 17 seconds in manual flight. During our autonomous flights, we were able to hit 100% of our waypoints within a 25-foot radius. Static obstacles, including the flight area perimeter, are entered into our Mission Planner waypoint courses as boundaries, which automatically tells the autopilot to avoid them. If the direct line path between 2 waypoints crosses over an obstacle, the path is manually updated to circumvent the obstacle. For moving obstacles such as other aircraft, one of our operators is tasked with monitoring the airspace around our plane. If we are heading towards another aircraft, the autopilot operator can activate a temporary RTL, which will cause the plane to turn away from its current position. After the airspace is clear, the waypoint mission can then be resumed.
This year, alternatives to our propulsion, structures, and image downlinking process were proposed. Our propulsion system was selected between an electric or gas-powered propeller. Previous years, ARC has used a gas-powered propulsion system due to its longer range. However, this year, an electric motor-powered propulsion system was opted for. While the range of our aircraft would be decreased, the risk of engine dead sticks could be eliminated. There is also no longer need for any engine tooling. The electric motor also proved to be more responsive to turns, being able to perform tighter maneuvers compared to a gas engine. One of our acceptance criteria for Kavik was ease of manufacturability. As such, while the idea of creating a full carbon fiber composite plane was proposed, the wood fuselage with carbon fiber wings and tails was decided upon. This set of materials proved to be easiest to manufacture considering the geometry of the different airframe components. We simplified the tail geometry in order to make the carbon fiber manufacturing process easier.
Lithium polymer batteries and a large propeller are our team's biggest safety threats. To reduce the risk of a battery fire, lithium batteries are stored and transported only in designated LiPo-safe bags or hard-sided containers. Batteries are only charged while under supervision and are returned to storage charge immediately after use. The propeller is the most dangerous element of our aircraft. To prevent accidents, the propeller motor is powered by separate batteries from the rest of our systems. These batteries are left disconnected until the plane is on the runway ready to take off. Only the safety pilot is allowed to connect these batteries, and only then when everyone else is clear of both the plane and the plane of the propeller. Some other risks while flying are onboard fire, collision with an object, or loss of control of the plane. These are mitigated with redundant safety systems and a pre-flight safety briefing.
Full mission testing is conducted at flight test with the members of our competition team, the safety pilot, autopilot operator, and ground station operator. Full mission tests successfully show that our aircraft system can fulfill all flight performance requirements. Here's a list of our confidence in accomplishing the competition's required tasks. Water bottles can be dropped successfully and land within the target zone about 50% of the time. The plane can successfully take off and land within a 600-foot runway. Estimated time to complete the mission is about 25 minutes depending on how many landings are required to swap batteries. The first video shows proof of manual control. The safety pilot takes off with a fully loaded aircraft and flies at least 1,000 feet away. Here, the plane is now 1,000 feet away from the safety pilot. The safety pilot now lands the aircraft, and all tasks to show safe manual flight are complete. The second flight demonstrates autonomous capabilities. Here, the plane is now 200 feet away from the safety pilot. The plane is now switched into autonomous flight mode, flying its course at least 200 feet away from the safety pilot. Here, the plane is switched back into manual control, and the safety pilot brings it in for a landing. The criteria for our autonomous flight demonstration are now complete. Third flight demonstrates the plane's ability to meet all flight performance requirements. A fully loaded manual takeoff is performed at an angle of climb of 20 degrees. The runway we use for flight testing is much less than 70 feet by 600 feet, so our plane satisfies this criteria. Right here, the plane is transitioned into autonomous flight mode, and the 5-mile flight begins. Mission planner statistics are provided to show that the altitude remains greater than 75 feet above ground level the entire time. Mission planner data also demonstrates the plane's ability to perform turns at a radius of 150 feet, its ability to hit waypoints with a max error of 25 feet, and its ability to stay within the mission boundaries. Here, the plane turns with a turn radius of 150 feet. Here, 5 miles have been flown in total, and the plane is brought in for a manual landing. The plane lands with a descent angle of 20 degrees, and all criteria are met. Proof of safe flight is complete. In summary, we are proud to show off Kavik after a year and a half of development. Kavik's primary advantages are its slower cruise and landing speed, which helps with the accuracy of payload drops and higher maneuverability. The payload drop system has seen a complete overhaul, which includes delayed release parachutes. Imagery has improved since last year with the completion of our imaging processing system and improved downlinking ability. Many quality of life improvements have been made, helping us set up and prepare for flight quicker. Thank you for watching our flight readiness review, and we hope to see you at our competitions at the flight line.